Hey everyone, this video is for section 9.3 where we're going to focus on hypothesis testing and confidence intervals for independent samples for two means. So first, independent samples. This is when individuals in one sample do not dictate which individuals are to be in the second sample. So for example, say we are working with married couples. We'll put one spouse in group 1 and we'll put their other half in group 2. So if we are randomly sampling from group 1, this would no longer be independent if we say we pick, we'll say Chris, and once we pick Chris, it forces us to pick Chris's spouse. Suddenly there is a dependence because depending on who I pick from group 1, that's going to force me to pick who I'm going to work with in group 2. So to keep going, we have two different groups. That give us a measurement for the same variable. So we're going to move to hypothesis testing. So I already have this laid out for the top because we've done this so often already. So x1 bar and x2 bar, this is going to be the mean measurement of n sub 1 randomly selected objects from group 1. And then if you kind of notice, after you put all that effort into, in this case, a very general description, we basically can kind of copy and paste, just adjusting, noting who is in group 2 for x bar 2, and then we can really still take that definition and dump the sample sizes and then just use the word all when we start moving into the parameter, which always connects to population. So parameter being mu1 and mu2. So when it comes to your hypotheses within your phantoms approach, it's very lackluster. It's almost kind of pessimistic when we are dealing with the null hypothesis because we're basically saying there's no change. They're exactly the same. Like, in a way, you're almost kind of like, why are we doing this? Like, they're exactly the same. So for the null, we would say something like mu sub 1 is equal to mu sub 2. Another way of looking at this, and I'm going to go ahead and write this on the side in red, we would say something like mu sub 1 minus mu sub 2 is equal to 0. And what I want you to be aware of is that this is saying the exact same thing. If, for example, we are claiming that mu sub 1 is equal to mu sub 2, in other words, they're the same, then if we subtract two values that are the same, then we're getting 0. So when it comes to the alternative hypotheses, this should not be a shocker that we are going to be using the same three inequalities that we've been working with this entire quarter. So again, when it comes to the alternative hypothesis, we're just going to drop down our two values. And then I'm going to come through and we could do a left tail test, we could do a right tail test, or we could do a two-tailed test. If you would like, you could also look at this from the perspective of a subtraction. So again, I'm going to go ahead and write the subtraction option in here as well. Oop. So let's go ahead and move on to our assumptions. I'm going to scroll this up. So for our assumptions, you should kind of note these are going to look very, very similar to the ones that you already explored. So the first thing, do we have simple random samples from both of our groups? This one is a little bit newer. It kind of connects with what we had just looked at in section 9.2, where the question there was, are the samples dependent on each other? Because we were looking at paired samples. Here we're looking at independent samples, so we are going to ask the question, are the samples independent? If you think about it, you're essentially asking the same question. You could just rephrase this checkpoint as, are the samples dependent or are they independent? For number 3, we want to know if the population is normal from each group. Or is each sample a sample size of 30 or greater without outliers? So ideally, we want to make sure that there are no outliers in there. If there are, then what I would suggest doing is defaulting back to your section 6.4 material and checking out the histogram of your data as well as the normal probability plot. So we would like to see a bell-shaped curve, and we would also like to see on our normal probability plot a relatively straight line without major deviations. So if we are given data, we need to use our checks from section 6.4 to see if normality can be assumed. And then lastly, for number 4, do you know the population standard deviation? So in other words, good old sigma. So if these assumptions are satisfied, then that means that we can use a 2-sample t-test. Now, before we jump into our calculator, I wanted to take some time to talk about some of the things that your calculator is able to do behind the scenes. I want you to be aware of that background information. So one of the first things that your calculator will automatically take care of for you will be the sample statistic. However, I want you to be aware you can easily do this by hand if you are interested. So we're working with x bar 1 and x bar 2. Remember, x bar just represents sample mean. This is where we're going to take all the values within the sample, sum it together or add it all up, and we're going to divide it by the total sample size. In other words, the total number of data points that we were given. And we would do this for group 1 and for group 2. Remember, in this hypothesis test, we're interested to see if there is some sort of difference or if there is no difference. So it seems logical then we would take both of those sample means and we would subtract them. Keep in mind that order is going to matter here. So in this case, we do group 1 first minus group 2. Now we come to our test statistic, or in other words, our t-score. The t-score will tell us how many standard deviations above or below the mean we are in a t-distribution. But what I want you to note here is that we essentially are working with the same structure of the z-score that we had worked on earlier in the quarter. So x bar 1 minus x bar 2, that's essentially the data value that you are working with. That's the specific situation that you got from the sample that you were working with. Mu sub 1 minus mu sub 2, that's the difference that we are assuming is happening within our population. However, what I want you to note here, if you refer to your notes, is that we claim that mu sub 1 minus mu sub 2 was equal to 0. So that's why if you come over to the formula on the right side, this is why we've essentially eliminated the mu sub 1 minus mu sub 2. Since it's 0, it just kind of goes away, and we're able to clear our numerator up a little bit. And then below, we have our standard error. And then again, you can see that the standard error is defined over on the right. And then, of course, since we are working with the t-distribution and we need to kind of determine the thickness of the tails on that distribution, we need to know the degrees of freedom in order to proceed. So you can see that the degrees of freedom here, it might take us a little while if we were calculating that by hand. And again, we would need all of this information in order to determine the area under the t-distribution. But of course, we do have technology to help us in this course, so we're going to focus on our calculator usage right now. So in order to obtain our p-value and actually our test statistics simultaneously, we are going to enter our data into list 1 and list 2. Remember that our data are going to be independent from each other, so there is no need for us to create a list 3 where we would have those differences kind of automated. So once we have entered our data into list 1 and list 2, we are going to go ahead and go to stat, and we're going to arrow over to option number 4, which is going to be a 2-sample t-test. Once you go in there, if you have the stats option, you would be entering in basically the sample mean, sample standard deviation, and sample size for each group. So those are the first 2 bullet points. You're going to indicate the type of tailed test that you're working with, And then you're going to have a new option that comes down where it's going to ask you if the information is pooled. We're going to select no. We would only select yes if we know the population variances are equal. So this is either going to be coming from you as common knowledge that you've picked up in your experience in life, or it's going to actually be presented, most likely will be presented in the narrative that you're working with. Finally, once you've done all that information, your test statistic will be presented to you along with the p-value. And it's basically the same song and dance that you have been doing this entire quarter so far. If your p-value is less than or equal to alpha, then we are rejecting the null and accepting the alternative. And then if your p-value is greater than alpha, then we fail to reject the null, and we do not have enough evidence in order to support the alternative. Just as a quick reminder, remember that we never say we accept the null. We're basically just saying, I couldn't find anything better, so I'm kind of stuck with this belief system right now. But rest assured, if I find evidence that allows me to dump it, I'm dumping it. Finally, now that you've made that general conclusion, we're going to go ahead and bring this into the context of the problem. So initially, what we will say is at the whatever level of significance we're working with, we maybe reject the null. And if we reject the null, that means that we do have sufficient evidence to support the alternative, and then we would include that information as to what the alternative was. If you need a reminder, that's why you're going to go back to the definitions that you've outlined for your parameter, and if you don't remember the alternative, go back to how you defined your alternative hypothesis. On the other side, if we say we fail to reject the null, that means we do not have sufficient evidence to support the alternative, and then we would add the context behind it. Okay, we're going to move on to the next video to talk about confidence intervals.